Okay, cool. So we're now recording. All right. And also, speaking of recordings, I did send out the email on Saturday, I believe, saying that all of the previous recordings were up. So in case you missed that email, and you missed a day in the past, you were absent for one reason or another, the recordings are now up. I did specify there was one class in particular where I forgot to record, and that was the last class before Thanksgiving break. So 11-20, you're not going to be able to find because I just didn't record it. So that one's on me. Sorry about that. So the couple boilerplate things before we actually get going on the math. First off, also in the email that I sent you guys, there's a 55%, last time that I was notified, there was a 55% completion rate of the student evaluations. Today's the last day that you can fill them out. So if you can do that for me, that'd be fantastic. I'd appreciate that. Again, like I said before, I spend all semester long grading you guys. It's only fair that you should have the opportunity to also grade me. So try to fill out the student evaluations, just with whatever constructive criticisms or things, even things that you liked. So that way I know for future classes, what to keep, what to get rid of, maybe what to change, things of that nature. Okay. Secondly, today is our final office hours, so I will still hold office hours today, starting at 4:15. Generally, the last office hour before the final exam is one of the busier ones. So if there are a few people, like if there's quite a few people who are there, I don't mind extending office hours a little bit longer today, but obviously that's basically dependent on how many of you show up. So we'll see what happens, but final office hours today, 4:15 p.m. I'm also going to do a once over of Blackboard one more time just to make sure that my Blackboard grades reflect the grades that I have in the grade book. So basically, everybody should be done with Blackboard. There shouldn't be anything else that's going up on there unless last week you had like a makeup or something like that, like a makeup quiz, in which case that still needs to be updated, and that's why today I'm going to be doing a one more time, one more through black through basically for everybody, just making sure that all the grades end up matching. So later today or tomorrow, look at Blackboard, just double check your grades, make sure it all looks good ahead of the final. If something doesn't look good, reach out to me. For the record, your quizzes don't include any bonus points on there. So all bonus points were just in my grade book, and that'll get tallied into your final grade at the end. And then the final thing is, right before the exam, I know a lot of people have this really, really, really big bad habit of trying to cram before every single exam. The best thing you can do, and I say this for every exam you take, not just algebra, but the best thing you can do is right the night before the exam, just get a good night's rest. Just getting a good night's rest is way better for you than trying to cram, because you're going to forget things, and the things that you already know are going to be harder for you to remember the next day anyway. So just try to get a good solid 8 hours sleep, eat a good breakfast the day of the final, and you'll be pretty prepared, or as prepared as you can, for the final. Okay? So try not to cram. Okay, so let's get to the actual questions that you guys have. So, Gabriella, question 14 of the review. Sure. Let's see here. Which one is 14? Okay, so 14 has to do with interest. So we were discussing when we were talking about exponential functions and even logarithmic functions, we were talking about interest. So there's continuous compound interest, and to use this formula because in the question it starts with assuming your investment is compounded continuously. That word continuously should let you know that you're using either this one, oops, which is the logarithmic form, and then there's also its its counterpart. I'm sorry, that's the exponential form, and then there's also its counterpart in the logarithmic form, which is the natural log of a divided by p is equal to RT. These are both equivalent. These are the same exact equations. It's just that if you remember when I described this to you, one of them is easier to solve for certain variables and one of them is easier to solve for other variables. We use the exponential form to solve for your final total or to solve for your principal amount, but trying to get your rate or your time out of this can prove to be a little bit more difficult, right? However, in the logarithmic form of the equation, notice how r and t are now linear. They're no longer attached to e as an exponent. So it's a lot easier to solve for your rate and your time in the logarithmic form of this equation. So the question says, assuming your investment is compounded continuously, how long will it take for you to double your money if your interest rate is a whopping 10%? Okay, so we don't necessarily know what we're starting with as far as a principal amount. So it's always good to list out your knowns and your unknowns. So your knowns in this case, well, P is P. We don't know what your initial investment is. But you do know that your final total should be twice as much as your principal. Why? Because, well, it says, how long will it take for you to double your money? What that means is at the end of this, by the end of this question, what we're trying to find is that however much money you put in, you should be getting twice that much out of it. So whatever P is, your final amount, A, should be twice as much as P. We know that our interest rate is 10%, or we could look at it also as 0.1. And then the last thing that we need to do is evaluate what we're actually looking for, which it says, again, how long will it take? So what we're looking for here is time. So time is our unknown. That's what we're trying to figure out here. So if time is our unknown in this case, well, we should probably use the logarithmic form of the equation, because the logarithmic form, notice how time, again, is linear, so we can solve for time by itself. Again, trying to solve for t over in this equation would prove to be a little bit more challenging. So, okay, great. We know we're going to use this equation. Let's go ahead and set up with everything that we already know. So setting up with everything we already know, let's just plug things in. So we have the natural log of, well, A is 2 times P, as we already established, right? A is 2 times your total. So we have 2 times your total over, 2 times your initial over your initial is equal to 0.1, because that was your rate, times T. Okay, well, we see we can do some cancellations inside that logarithm, right? We have P over P, so we see that, this is going to cancel out with that. So it actually doesn't matter what your initial investment is, because notice how in the logarithm it's canceling out anyway. So whether it's $1,000 or $1 million, it's always going to cancel out here. So now we can have the natural log of just 2 is equal to 0.1 times time. And when we want to solve for time, that means dividing by 0.1. So we divide by 0.1. So we have the natural log 2 divided by 0.1. And I know that over the course of the semester, I've said, try to use fractions instead of decimals. It's generally, going to help you out in most situations. In this situation, it doesn't necessarily matter. But if you wanted to be consistent with what I was saying, instead of 0.1, you would use, 1 over 10. But either way, however you want to write it, just make sure that you're being consistent and make sure that, every step that you're making is still mathematically equivalent. So we divide by 0.1 on both sides, or by 1 over 10 on both sides, however you want to think about it. And then we get t all by itself. So t is all by itself now. So if we wanted to figure out what this natural log is, and I specifically said in the question, you probably need a calculator for the first question. Did anybody calculate this? Or does anybody have a calculator off the top of their head, that they can just enter this in? P.S. Today's the last day for participation credit. Just throwing that out there. So what I'm looking for is just natural log of 2 divided by 0.1. But it's okay. I can absolutely get the answer for that as well. 6.9. Perfect. Great. So 6.93. Thank you, everybody. So 6.9. We'll just say about 6.93. Okay, so we'll leave it like that. So what this tells you is that, and again, remember that t is measured in years. So this tells you that it takes you just under 7 years for you to double your money at 10%, when your interest is being compounded continuously. It doesn't matter what your initial investment is, it's always going to take you 7 years. Whether it is, again, $100, $1,000, or $1 million, it's always going to take you 7 years to double your initial investment. Okay, so great. So we figured out the first part of the question. Now, the second part of the question says, what if the same question is posed, but with simple interest instead, which takes less time? So what we have to do is we have to essentially set up the same question all over again, but this time with simple interest. And then we're going to see what we get for simple interest as far as, how much time it takes with that setup. And then we'll compare it to this right here. So let's leave this boxed. So we have t is equal to 6.93. We're going to leave that over there, and I'm just going to draw a line over here. We're going to set up simple interest. Now remember, simple interest is, well, it's in the form I is equal to P times R times T. Remember that simple interest is entirely linear. There's no exponential stuff going on. It's just your initial investment times your interest rate times time, right? And if we remember, your total amount of simple interest is P plus I, right? It's your initial amount, which is P, plus your interest that you accrued, so P plus I. I'm going to replace I with what we just, with what we know interest is in regards to simple interest. So I'm just going to say, okay, well, our total, A, is really P plus P times R times T. Okay, so at this point now, what I'm going to do is I'm going to substitute in the things that we know. Remember that we don't necessarily know what our initial investment is, but that's not necessarily that important, and we'll see why again in a second. We do know that our total amount should be twice our initial amount, right? So we know that A should be 2P. And we know that the rate, once again, is 0.1, and that T is what we're looking for. So let's go ahead and fill that stuff in. So we have P plus P times 0.1 times time, right? We're looking for time. Okay, so notice we have a P in the first term and a P in the second term, right? So if I want to factor out that P, because if I factor out that P, I can divide both sides by P, right? And then your principal amount is just going to cancel out. All I'm doing right now is I'm just trying to get T all by itself. So my process is move all the other stuff over, right? So what I'm going to do is, okay, we're going to leave the 2P over here. We're going to factor out a P from both terms. So if I take P out of P, then I just have 1 left. And if I take P out of the second term, well, then I just have the 0.1 times time. And so now it becomes really easy to see that I can just divide both sides by P. So dividing both sides by P, this means, okay, well, these are going to go away. And if you saw it in the above step, if you saw it right here that you could just divide all 3 terms by P and you'll get the same answer anyway, then totally, that's absolutely fine. I just, did the factoring step just to show that, this is what my agenda is here. Okay, so now notice that your principal amount no longer exists in this equation. We're left with 2 is equal to 1 plus 0.1 times time, right? So your principal amount, once again, doesn't necessarily matter when we know what we're supposed to end up with. We know we're supposed to end up with twice your principal amount, so it doesn't actually matter what that specific value is, because notice how it's dropping out anyway. So, okay, all we have left to do is just solve for T. So solving for T means, okay, well, I have this addition of 1 going on, so I'm just going to subtract 1 from both sides. So I have 1 is equal to 0.1 T. And now solving for T, divide both sides by 0.1. So you have 1 divided by 0.1. So 1 divided by 0.1 is equal to T. And 1 divided by 0.1 is 10. So you get T is equal to 10. And so now what I'm going to do is I'm just going to call this one T sub S, just to show that this is for simple interest. I'm going to go back over here and say this is T sub C, which, again, to denote that this is for your continuous compound interest. And now notice how when you're comparing the one that we first solved for versus the one that we solved for just now, the one that we solved for first is way shorter, right? It takes a little over, or I'm sorry, yeah, it takes like 3 years less to double your money than it does if you were doing simple interest. And that's all there is to it. It takes 10 years to do it for simple interest, like 10 years exactly, whereas for continuous compound interest, it's a little less than 7. And that's all the question was asking of you. Does anybody have any questions on this, on how, we set this up? How did you get 6.93 from this beast right here, natural log of 2 divided by 0.1? So our idea was we used the natural log of the continuous compound formula, right? So there's 2. We used the natural log version of it because we are trying to solve for time. So when you're trying to solve for rate or time, you use the log version. When you're trying to solve for A or P, you use the exponential version. Okay, then we just plugged in all of our knowns. We saw that our principal amount canceled out. So when we have natural log of 2p over p, well, p's cancel out, so it's just natural log of 2. And then solving for t, you just divide both sides by the 0.1. So t is now all by itself. And when you plug this into a calculator, as I asked, a couple people to answer for me before, you get 6.93. And it's it's an irrational number. It's going to go on forever, but it's approximately 6.93, which is fine for the purpose of this question. And then over here, the idea is, again, we know this. So boxing that off, this just has to do with simple interest. So your interest is defined by your principal amount times your interest rate times the time, the amount of time that you're putting it in. And then your total is your initial amount plus whatever interest you've accrued. So I just plugged in the, what we know for interest into our total formula here, and then factored out the p so I could divide it from both sides, because I have a p on my left side because that's what our total amount was dependent on. Our total was twice of our initial investment, and then we have p over on the right hand side because that's just part of the normal equation. So dividing it out means that, oh cool, it actually doesn't matter what my cancel regardless. So we see that it in fact does cancel regardless. We divide p out from both sides, and then it's just a simple matter of solving for t. And solving for time, once again, leads you with 1 over 0.1, which is 10. Any other questions on this? Okay, so just make sure you remember going into the final these 2 different formulas for your continuous compound interest. It's continuous compound interest. To use these formulas when you see the word continuous, right? That's what is indicative of E, if you remember, when we were first discussing exponential equations, or exponential functions, rather. Okay, so that was number 14. Let's jump to Keji's question number 7. Okay, I'm going to go ahead and clear this off here. Number 7, let's see what we have. Number 7 has to do with trig values and trig angles, and this is all basically like of the most recent chapter here. So it says if theta is an acute angle of a right triangle. And so for the record, if you ever see that opener, that disclaimer in the beginning, if theta is an acute angle of a right triangle, all that's really meaning to tell you is that theta is not the right angle. So there's 3 angles in a triangle. Obviously, this is basically just saying, hey, this is one of the smaller ones. This is not your right angle. So if we draw a right triangle, it's basically just saying, hey, don't pick that corner to be theta. You can pick either of the other ones to be theta, but just not the right angle. So if theta is an acute angle of a right triangle, and theta is equal to 30 degrees, so let's go ahead and put theta right here in this corner here. And I'm just going to put it right above. Theta is equal to 30 degrees. Okay. Now what it wants us to find is cosecant of pi minus theta times cotangent of pi over 2 minus theta. Sorry, did I say pi minus theta? I meant to say pi over 2 minus theta. Sorry about that. So we have, and I'll just write it down one more time. This is what we're supposed to find. Cosecant of pi over 2 minus theta times cotangent. Cotangent of the same thing, pi over 2 minus theta. Okay, so before we even get started, this right here, these this specific measurement here should be ringing a bell in your head, because this was literally the last topic of the last lecture that we covered. Cofunctions, right? There's cofunctions, so there's pairs of these trig functions that if you are starting with, like sine, for example, you can always convert it to cosine because cosine is the cofunction pair of sine. So you can always go from sine to cosine or vice versa by taking whatever your starting angle is and subtracting it from 90 degrees, right? Well, pi over 2 in radians is 90 degrees. Pi over 2, we already established this is, absolutely equivalent to 90 degrees. If we were to draw, our our axes here, right? This is 0 degrees or 0 radians, however you want to think about it. This over here is 90 degrees, but it's also, you could define it as pi over 2, right? So with that being said, we know that this is essentially just saying, okay, well, it's cosecant of 90 minus theta. Well, it doesn't necessarily matter what your theta is. You know this to be true. If you are starting with secant of theta, this is the same thing as cosecant of 90 degrees minus theta, right? And that's what we have right here. We have cosecant of, 90 minus theta. So if you wanted to, you could absolutely simplify this off the bat with cofunctions. You could say, okay, well, this is just secant of theta right here. So just writing it above, you could simplify this to say, okay, well, this is secant of theta. And then the same thing can be said for cotangent. The cofunction pair of cotangent is somebody? Anybody? So we have cosecant and secant being cofunction pairs. What's the cofunction pair of cotangent? Yeah, thank you, Grace. Tangent. Exactly. So the same thing is also true. If you have tangent of theta, this is the same thing as cotangent of 90 minus theta, right? So again, notice this is what we're given. We're given cotangent of pi over 2 minus theta, or 90 degrees minus theta. So you could just also replace this one with tangent of theta. So you've already simplified this a little bit if you wanted to. If you wanted to use cofunctions, you could absolutely do it this way. But we were given what theta is, right? Theta is 30 degrees. So as long as you just convert your pi over 2 to 90 degrees, as long as you convert your radians to degrees, you should be fine. You could just plug in theta. So you would have 90 minus 30 right here. And then, okay, so 90 minus 30 is 60, and that's, you could absolutely find cosecant of 60. Same thing could be said for cotangent, right? You could find cotangent of 60 as well, and then just be advised that your angle, your theta, is still 30 degrees, right? So if you did use cofunctions, then instead of having 90 minus 30 for secant, it would just be secant of 30, right? And this should make some amount of sense. Oops. I just closed out a whiteboard. Am I still sharing? Yeah, okay, great. Secant of 30 degrees is equivalent to cosecant of 60, right? Remember that for cofunctions, it's essentially the complementary angle. They should add up to be 90 degrees. That's what we found. That's what this 90 minus theta is telling you. Whatever your starting angle is, the cofunction pair of it is just going to have the complementary angle of that. So if 30 degrees is our angle, then we could say, okay, well, then cosecant of 60, again, like we just simplified from the 90 minus 30, but you can get the same thing from just secant of 30 degrees. These are equivalent statements. It's just, different trig function, slightly different angle. Okay, so regardless how you go about it, what you need to do is, well, you need to find the, some sides, right? So basically, we just need to figure out here what's going on. So cosecant, if we're talking about sides of this, triangle, we're just going to call them A, B, and C. And I feel like this is probably what threw most of you for a loop, not actually having the, the sides in front of you. Just call them something. In practice, on an actual exam, I would add, I did it again. I closed whiteboard. In an actual exam, I would give you, numbers for, to figure out here. But just in this case, because there are no numbers, you just have to just call the sides something, and then you can figure out what everything is, right? Okay, so let's go back to whiteboard here. Let me start sharing again. Sorry about that. It's not going to let me share. Why not? Okay, that's fine. I'll just share my screen. Okay. Okay, so Kenny, are cofunctions always double of each other? No, remember, cofunctions are, there's certain cofunction pairs, it's always the complementary angle. So that doesn't mean double, that means 90 minus whatever your starting angle is. So just as a quick example, if you're given sine of 20 degrees, then what you have for cosine is cosine of 90 minus 20. And which obviously simplifies down to be cosine of 70. Notice how 20 and 70 add up to be 90, which again, complementary angles, right? So it's, you just have to remember the cofunction pairs, and whatever angle you're given, the opposite pair of it should just add up to be 90 degrees. But good question, though. Definitely, we have to remember that because we didn't spend too much time on it. Okay, so we don't necessarily know what these, what the sides are, but we do know that theta is 30 degrees, right? And because we know that this is a right triangle, we also know then that this angle is 60 degrees. So if we have 30 degrees, 60 degrees, and 90 degrees, we have a 30, 60, 90 triangle. So 30, 60, 90 triangle. Who remembers what the proportions are of my sides here? What should this side be right over here? Since it's opposite of 30 degrees. What can we call that instead of B? I mean, you could call it B, that's fine. But, what did we generally call it? Just so, we could find the relationship of the other sides. The side opposite of 30 degrees in a 30, 60, 90 triangle. Yeah, we called it A, right? So again, it doesn't necessarily matter what letter you call it, but in practice, we called it A. Okay, then knowing one side, we can find the other two sides because again, we know that it's always going to be proportional, right? In a 30, 60, 90 triangle, we can figure out the other two. What is my hypotenuse? What's always the length of a hypotenuse in a 30, 60, 90 triangle?
2A.
2A, yeah, it's 2 times whatever your shortest leg is, right? So 2A, and then I'll just do the last one. The last one, the side that's opposite of 60 degrees, is your shorter leg times square root of 3. So we know this to be true. It doesn't necessarily matter what A is. We know that it's always going to be in these proportions, right? Your hypotenuse is always going to be twice the size of your smaller leg. Your longer leg is always going to be square root of 3 times a longer, right? So with that being said, I'm just going to go ahead and erase some of the work here that we were doing before. So with that being said, well, let's just try to find now what these things are, right? So if you're doing it the way in red, where you simplified using cofunctions, we'll do that in just a second, just to show you that you come out with the same answer. But let's just do the pieces in black first, what we were actually given. So cosecant of pi over 2 minus theta. Well, again, this is in terms of radians. Hopefully you all remember how to change radians over to degrees, but I just kind of expect you to know pi over 2 is 90 degrees. If you don't remember, though, what you do is you take your pi over 2 and you multiply by 180 over pi, right? This should convert any radians to degrees. Why? Well, we see that the pi's cancel out, and then we have 180 over 2, which, hey, that gives you 90, right? So even if you forgot pi over 2 is 90 degrees, as long as you remember how to convert back and forth between degrees and radians, you're still in good shape. So what this says is you have, okay, cosecant of 90 degrees minus 30 degrees, because we know theta is 30. So you have cosecant of 60. And then over here, cotangent of the same thing, 90 minus 30, which is 60. So you have cotangent of 60 degrees. Okay, well, now we just have to figure out what cosecant of 60 and cotangent of 60 are. So what's the relationship of cosecant? What's the side relationship? You could also tell me what the inverse is. What trig function it is the inverse of or reciprocal of. Anybody? So what I'm looking for here is just the side relationships. You don't have to tell me what actual sides they are just yet. I just want to know what cosecant, how you find cosecant. So careful, it's not going to be, so the only relationship that secant and cosecant have is that they're cofunction pairs. So just like, we talked about how we converted this piece in black here to the piece in red, then that's, using cofunctions. But it's not going to be the reciprocal of secant. It's the reciprocal of one of our three starting trig functions, right? We have sine, cosine, and tangent, and then cosecant, secant, and cotangent are reciprocals of those, right? So what I'm asking you is, what is cosecant the reciprocal of? Well, think about it. Cotangent is going to be the reciprocal of tangent, right? We can pretty much figure that one out. So we just have to say, okay, is cosecant related to sine or cosine? Yeah, Gianna, thank you. Cosecant is going to be the reciprocal of sine. So if you know then that sine of theta, whatever theta is, it doesn't necessarily matter. If you know sine of theta is the relationship is opposite over hypotenuse, you know then that cosecant being the reciprocal of it, cosecant of theta should be hypotenuse over opposite. And that's all I'm looking for. I'm just looking for you to, figure out how to find cosecant regardless what the angle is. It's always going to be your hypotenuse over opposite. For secant, it should be, well, hypotenuse over adjacent because it's the reciprocal of cosine. So now we know we need to find hypotenuse over opposite, right, of whatever our angle is. So in this case, we're talking about angle 60, so 60 degrees. So we look and we say, okay, so here's our 60 degrees. We need to find the hypotenuse over opposite. Well, hypotenuse is always going to be the hypotenuse, and that's always, in this case, 2 times a, right? So we can say, okay, well, we're starting with 2a over, and then what's the opposite side of 60 degrees? Well, that should just be a square root of 3, right? It is opposing 60 degrees, so we know then this goes into our denominator. So a square root of 3. And we'll throw that in. And before we do any simplifications, let's just do the same thing since we're still looking at cotangent as well. And we're looking at the exact same angle. So we're still looking at this angle here, angle 60. So in red, this piece right there. So we're looking now, tangent is opposite over adjacent. So cotangent being the reciprocal of it should just be adjacent over opposite. So the side that is adjacent is A, and then the side that's opposite, again, just like we established from before, is still a squared root of 3, right? So setting up this fraction should just be, again, instead of opposite over adjacent, it's adjacent over opposite. So we have a over a squared root of 3. Okay, so now all we have left to do is just simplify. So we have an a on top and bottom of both of our fractions, so we can cancel all the a's here. So the a cancels here, the a's cancel here, and now we just essentially have, just to simplify this a little more, we have 2 over square root of 3 times 1 over square root of 3. Well, this isn't so bad. It's just fraction multiplication, right? We can just go ahead and multiply across. So multiplying across, we have 2 times 1 up top, so we have a 2 up top, and then square root of 3 times square root of 3, which gives you square root of 3 squared, or square root of 9, however you want to think about it, and that's just going to give you a 3 on the bottom. So when all is said and done, cosecant of pi over 2 minus theta times cotangent of pi over 2 minus theta just gives you 2/3. And again, we got that just from knowing that theta is 30 degrees. And now notice it doesn't matter what the sides of your, the lengths of your sides are. I didn't give you any specific numbers. There's, it doesn't say, 5, 20, 17, whatever. All we were able to figure out was just deriving it from the fact that it is a 30, 60, 90 triangle. And because of that fact, we knew the relationship of each side to, every other side. So the smallest side being A is opposite your 30 degrees. We knew that that side was A because it opposes theta. And again, we were given that theta is 30 degrees. And then given that knowledge, we can figure out the lengths of the other two sides. Hypotenuse is always twice that. And the longer leg is square root of 3 times, the shorter side. And then it's just a matter of plugging things in, simplifying, and you get 2/3 as a result. And now just real quick to show you that you can in fact do the same exact thing in red. So if you use cofunctions to simplify, you got secant of theta and tangent of theta. So I'm just going to show that real quick. Is it okay that I just used the chart from the lecture and did the reciprocals and just plug them right in? Sure. Yeah. I mean, if you can derive the chart on the fly, absolutely. It's just that, obviously in this case, we didn't have the chart in front of us. So what we did was we used the triangle to figure out the necessary part of the chart that we needed. Remember that the chart from the lecture was derived from the two triangles, right? The 30, 60, 90 triangle and the 45, 45, 90 triangle. So basically utilizing the chart is the same thing as utilizing the triangles, which is what I just did. So yeah, sure. If you want to just, if you can remember the chart entirely for the final, great, sure, why not? So that's absolutely fine. So again, just to show this, so secant of theta and tangent of theta, right? We figured out that those were the cofunction simplifications, right? And we know that theta is 30 degrees. So this is really the same thing as writing secant of 30 degrees times tangent of 30 degrees. And we should end up with the same thing, right? Secant should be hypotenuse over adjacent. So this should be 2 times, and again, we're talking about 30 degrees here, so we're talking about theta. So just to get rid of that, we're talking about this angle now here, theta, which is 30 degrees. So again, secant is hypotenuse over adjacent, so this should be 2a over a squared of 3. So 2a over a squared of 3. And then for tangent of 30, it should just be opposite over adjacent. So opposite of theta is a. And adjacent, as we just described, is a squared of 3. But wait, this is exactly what we had here to begin with, right? 2a over a squared of 3 and 2a over a squared of 3. A over a squared of 3 and a over a squared of 3, right? We get the exact same fractions, which should make sense because they are, of course, cofunctions, right? So all you did was, if you use cofunction identities to simplify down, you're going to get the exact same fractions regardless. And when, you do all the work, you still end up with 2/3 as your answer. Okay. Any questions on this? I just want to make sure that we're all good. Number one, with understanding cofunctions here, and number two, even if you didn't use the cofunction way, which is totally fine, that we understand how you can derive this triangle with just knowing the fact that it's a right triangle and knowing one of the angles is 30 degrees. Okay. So I'm going to take it as you guys are all good with this one. So if you guys are okay, then sure. We still have about 12 minutes left of class. Any other questions you guys want to go over? It doesn't necessarily have to be from the review sheet, but if there are more from the review sheet, then sure, absolutely. Number 2. What's number 2? Okay, so number 2 is a pretty important one because we only spent a little bit of time on it, but it's really not that bad. So it doesn't specifically say how to solve it, but that's kind of the point. It's, this is expecting you to remember how to solve it. So number 2 is asking you to basically remember intermediate value theorem, or IVT. What intermediate value theorem says is if you're given some function and you're given an interval, you can test to see whether or not there is a solution in that interval just by plugging in the 2 endpoints of that interval. If the sign changes of your output, dependent from, one input to the next input, if your output changes signs, then you do in fact have a solution, right? So another way, remember that I did that stupid diagram in the lecture where I, said you have to cross the road to get to a pizza place. It's that same thing all over again. So our function here is f of x is equal to negative x cubed minus 6x plus 3. And the interval that we're given, so the interval that we're given here is that we have to test over is from 0 to 1. Okay, so what we just have to do is essentially, if we're going to try to show that there's a solution in this interval, we just have to plug in the 2 endpoints of this interval. If we can plug in the 2 endpoints of this interval and the sign changes of f of x, then we've shown that there's a solution. So you just say, okay, well, f of 0, is equal to, you plug in 0 for everywhere, so you have negative 0 cubed minus 6 times 0 plus 3. That's a 0. And what this simplifies down to, you have 0 minus 0 plus 3, right? 0 cubed, or negative 0 cubed, either way is 0. Negative 6 times 0 is still 0. So you just end up with this plus 3 hanging around. So f of 0 is a positive 3. Now let's go ahead and do f of 1. So f of 1 is negative 1 cubed minus 6 times 1 plus 3. Well, negative 1 cubed, remember, a cube should just retain its negative value. So negative 1 times negative 1 times negative 1, you still end up with a negative 1. Negative 6 times 1 still leaves you with a negative 6 plus 3. And I mean, it doesn't necessarily matter what your value is, but we can finish this up. Negative 1 minus 6 gives you a negative 7 plus 3 gives you a negative 4. The important thing is this sign. So notice how the sign flips. It was a positive 3 and it flipped to a negative 4. That tells you that somewhere in this interval, somewhere between 0 and 1, I can't tell you where, there's not enough information here to tell you where it happens, but somewhere between 0 and 1, there is in fact a solution to this function here. It essentially says that it crosses the x-axis at some point here. And how do you know that? Well, remember how f of whatever is always going to be your output. So if you have some sort of function, let me draw it a little bigger. If you have some sort of function here and, you're hanging around down here, notice how the function up until this point is negative, right? We're talking about this, the output of it is negative. So as a result, we know then that the sign here is a minus, right? But as soon as it crosses the x-axis, notice that the output is now positive, right? The y-axis component is a plus, which means x is positive. So what this basically says is, okay, somewhere between here and here, if I gave you this interval, for example, it's crossing the x-axis. And that's, that because, again, the sign of f of x is changing. It went from a negative to a positive. And that's all intermediate value theorem is saying. Okay, so all you had to do is just plug in the two endpoints of the interval, see that the sign changes, and just say, yeah, by IVT, there's a solution. Okay, any questions on this before I move on? I'm trying to shotgun as many questions as I can, but I don't want to go too fast to where I'm, ignoring any questions that you may have. Okay, let's move on to number 10 then. Number 10, let's see. So number 10 says, all right, so this is the exponential function. We actually did 2 homework questions on this and a quiz question on this. So this one, I know that we spent a decent amount of time on this and also 1 lecture classwork on this as well. So there's definitely some good examples. If you don't understand what's going on here, for you to draw back from, just look for the exponential function lecture and you'll find examples of this. But we'll work through this one together. So we're given 2 solutions. We have 1, 3, and we're also given 2, 9. And what we're trying to find is a function f of x in the form of f of x is equal to c times a to the x. And oh yeah, a to the x, this should be indicative of an exponential function, right? Your input is an exponent, it's an exponential function, and that's all there is to it. So we're trying to find a function in that form. Well, okay, there's 2 unknowns here, right? We don't know what c is, and we don't know what a is. X is always going to be X. It's always going to be your input, right? So we're not trying to solve for X. You're trying to solve for the 2 other pieces here, C and A. So what we're going to do is, given our pieces of information, we're going to set up 2 different equations. And using those 2 different equations, we're going to solve for both C and then also for A. So we're given the first one, the first solution here, which is 1, 3. So that tells you that X is 1. And when X is 1, f of X is 3. So you have 3 is equal to c times a to the first power. Okay, well, c times a to the first power. A to the first power is just a, right? So this is the same thing as 3 is equal to c times a. And now you just solve for one or the other. In this case, I'm just going to solve for C, but it doesn't necessarily matter. You could solve for A, and you'll get the same answer regardless. So solving for C here just means divide both sides by A. So that means I have 3 divided by A is equal to C. Okay, sure, no problem. So now we have some value for C, right? Now what we're going to do is we're going to set up the same type of equation, but this time we're going to set it up for the solution to 9. So what that means is, again, x is equal to 2, and when x is equal to 2, your output is 9, right? F of x is 9. So what this says is, okay, we set this up one more time. We have 9 is equal to c times a, and x was supposed to be 2, right? So a squared. And when we plug this in, we actually can go ahead and plug c in, right? We know c is equal to 3 over a. So we have 9 is equal to 3 over a times a squared. Well, we can do the simplification here. We see that there's a division of a, and we have an a squared. So one of these a's is going to get knocked out. So instead of a squared, we're just left with a. So we have 9 is equal to 3 times a. And solving for a, we have 3 is equal to a, just dividing both sides by 3. Now that we know what a is, we can go back and solve for c. We can get an actual value for c here. So we know a is equal to 3. C is equal to 3 over a. We know, again, a is 3, so we have 3 over 3. And so c is just equal to 1. And so when we write our final answer here, f of x is equal to, and again, it was supposed to be in the form c times a to the x. We can just write f of x is equal to, c was 1, a was 3, so 3 to the x. And that's your final solution here. Hopefully this is ringing some bells in your head as far as, drawing references from what we did before. So all we're doing is just setting up 2 different equations in the form that we wanted, right? We wanted this form, so we set up 2 equations in that form. We use the solutions 1, 3 and 2, 9 to set up 2 different equations, because you need 2 different equations to solve for 2 different unknowns. As a general rule of thumb, you need an equation for each unknown that you have. So if you only had one unknown, you would only need one equation to solve for that one unknown. We had 2 unknowns, c and a, so it would make sense that we need 2 equations derived from 2 of the given solutions that we had. Okay, so we end up with f of x is equal to 3 to the x. Yeah, no, it's not super bad, but of course, it's good to get a refresher in, because we haven't done that in a while. And then I think the last question that I might be able to get in here, I might not be able to do the whole thing, Olivia, but I can at least get you started and get you going here for how you're supposed to handle it. So Olivia asked for number 3. I know that it's 11:48, so I'll get as far as I can, and then, for whoever wants to stick around, I'll try to, get through it. So number 3 says we have 5 over x minus 1 is less than or equal to 6x plus 24 all over x squared plus 4x minus 5. Okay, so for this one, this should actually resemble, not closely, but it should, you should be able to think of number 3 from the project packet, because this was, the kind of the same exact mentality, right? You have to solve using test points. How do you know you need to use test points? Well, number 1, the directions tell you need test points. But number 2, even more than that, you see that you have a rational expression. Well, technically you have 2 of them, right? A rational expression is just a fraction of polynomials. So we have a rational expression and we have an inequality. When you have a rational expression and an inequality, you absolutely need to use test points every time, no matter what. Okay? So to solve using test points, things have to be factored, right? And you also want one of your sides to equal 0. The reason you want one of your sides to be 0 is that when you go to do test points, then you can compare and say, okay, well, is it bigger than 0 or less than 0? And obviously that means, is it positive or is it negative? So what we want to do just to start off is we want to make one of the sides 0. I'm always partial to taking the smaller fraction and moving it over. So that means I'm going to move over the 5 over x minus 1. So I'm going to subtract that from both sides. So subtracting it from both sides, I have 0 now on the left-hand side, and I have 6x plus 24 all over x squared plus 4x minus 5 minus 5 over x minus 1. Okay, first step taken care of. We now have a 0 on one of the sides. That's what we were looking for. The next step that we have to do is we want to factor things. We want to get things fully factored so that way we know what numbers we're putting on our number line so we know what intervals to test. Well, to factor, we have to recognize we have a subtraction of two fractions here. So we need to get the fractions, together before we can even think about, getting this fully factored. Well, to get fractions together, we need a common denominator. So we have an x minus 1 over here. Let's see what happens if we factor the denominator of the other fraction. So that way we can, try to hope to get a common denominator. So we have 0 is less than or equal to, let's go ahead and just keep this as 6x plus 24. You can factor the top as well. It's no problem if you wanted to. And factoring the bottom here, well, you have x squared plus 4x minus 5. Can anybody help me factor this real quick? I'm just going to write over here 5 over x minus 1. So how do I factor x squared plus 4x minus 5? X plus 5 and x minus 1. Yeah, solid, right? And the way that you got there, Olivia, was you looked at -5, and you said, okay, I need two numbers that multiply to give me -5, but add to give me a +4, right? The +4 being right here. So two numbers that multiply to give you a -5 and add to give you +4 are +5 and -1. So, all right, cool. Let's write x plus 5 here and x minus 1. Okay, so with that being said, we have an x minus 1 here and here. So all we need to multiply by on the right-hand fraction is x plus 5 on top and bottom, and that should give us a common denominator, right? So I'm going to multiply x plus 5 on the top and on the bottom. And now we should have common denominators. So writing this one more time, we have 0 is less than or equal to 6x plus 24 all over x plus 5 times x minus 1 minus 5 times x plus 5 and x plus 5 over x minus 1. Or I'm sorry, x plus 5 times x minus 1. Sorry about that. And so now that we have common denominators, we can go ahead and combine things together. And because we have this 5 and, this x plus 5 going on business, we should try to factor this over here as well, the 6x plus 24. Or alternatively, what we can do is we can also go ahead and distribute the 5. So let's go ahead and distribute the 5 and see how that ends up working out. So distributing the 5, and just in the essence of time, I'm going to move a little bit faster here. We're going to keep the denominators the same because we're going to combine the fractions. So x plus 5 times x minus 1 in the denominator. We're combining fractions here. We have 6x plus 24. Now we have a negative sign, right? So don't forget to distribute the negative sign, but 5 times x and then 5 times +5, right? So 5 times x is a positive 5x, but we have the negative sign, so it becomes minus 5x. And 5 times 5 is 25, but remember the negative sign makes it minus 25. Okay, we're almost done. Let's go ahead and finish this up. So simplifying the top, we have 6x minus 5x, which leaves you with 1x up top. You have a positive 24 minus 25, which leaves you with x minus 1. And so you have x minus 1 over x plus 5 times x minus 1. And again, with the interest of time here, I'm going to stop here. But before I stop, I will just say, can you cancel the x minus 1 over x minus 1? Are you allowed to cancel those terms or those factors in an inequality? No, you cannot. Thank you, Jack. You absolutely cannot cancel those, because if you cancel those, remember the next step that what you're going to do, now that this is fully factored, there's nothing else for you to factor. You would set the top and the bottom factors equal to 0, right? So you would set x minus 1 is equal to 0, x plus 5 is equal to 0, and we have another x minus 1, which I'm not going to write. So when you solve for them, you would get x is equal to 1 and x is equal to -5, right? If you cancel the x minus 1s, you're canceling this piece here, which means you wouldn't be jotting down x equals 1 on your number line. So you'd essentially be cutting down the total number of intervals that you're testing from 3 to 2, and that would not be correct. Okay, so do not cancel your x minus 1s, but at this point, things are fully factored. You would put on your number line here, Why is it still in red? You put on your number line, -5, 1. You would have to establish whether or not you have open circles or closed circles on them, and then you just test your 3 intervals. Okay? Any questions on this? Again, I don't want to keep you guys too long. I know it's 11:55 now, and some of you guys have classes right after, so any other questions? All right, everybody. So that's it. That's literally it for our classes. I'm going to end the recording here. We have office hours again, as a reminder, today, 4:15 p.m. If you can make it, feel free to lob over any last-minute questions that you may have if you can't make the office hours. And I wish you best of luck studying, not just for my final, but for all your finals. Okay? So good luck, guys. I will see you on Wednesday. Remember your final time, Wednesday. What time? 11 a.m., just like all of our regular classes. Okay? Have a good one, everybody.